Welcome all of you to Physics for All by Shilpy Bhullar. We are doing video lecture series based on vector analysis, and today we are going to discuss curl of a vector function, its physical significance. In the previous video, we did the most important theorem, which is Gauss divergence theorem. It's one of the most important theorems in vector analysis. But now it's the time to understand curl of a vector function. A little bit of introduction regarding curl of a vector function we have already done. We know that curl means rotation. If a vector field is rotating, then we say that it's curling, and curl of that vector field is non-zero. As you can see these pics, please don't get scared by these pics of whirlpools, but there is a reason to show these pics because they all are showing curl. If we consider water or the velocity of fluid flowing as a vector, or even the wind that is flowing or the tornado that you can see as a vector, because obviously they have some magnitude and they have direction also, so we can consider their curl. As you can see in this pic, this water layers, you can consider it to be vector, and they all are moving. They are rotating. You can see these layers are clearly giving us the idea of the direction in which the vectors are moving. So this is a clear indication that here the vectors are curling. They are rotating. Same here in this pic. See, the vectors are coming and they are just curling inwards. They are rotating, right? So this is the clear real life example of curl of a vector function. Similarly, this thing, the water going down through the sink, this we would have seen like so many times, but we just never pay attention. This is again the example of curl. When sometimes the water gets blocked, or it just when there is huge quantity of water flowing through the sink, then we see that it simply curls. It curls and it just goes through these tiny holes. Same for the wind. You can see that all these wind particles or the wind that is blowing, it just curls, and it's just curling like this, and it gets pointed when it moves toward the ground. There is the example of rotation. We can see the real life rotation examples. So when something is having magnitude and direction, and in particular it's rotating or curling, then we say that curl of that particular vector function is non-zero. Thus, curl of a vector field signifies the circulation or rotation of the field. If something is moving in circle or something is rotating, and also we can see that it keeps on converging. Usually in curl that we see in real life, we see that the vector fields are coming and they are just rotating, and they just kind of converge to a narrow point. In all these examples, you can see that the vector is curling and then it's converging also. Though we understood the example of divergence also using the example of sink, the water flowing through the sink, we know that when water flows through the sink, it is example of negative divergence. But if we say that the water is rotating as well, then we say that okay, that particular vector function is showing both divergence and curl. So in this particular example of water flowing through the sink, here both divergence, suppose v the velocity vector, so both divergence and curl are non-zero. Divergence y is non-zero because here it's the example of negative divergence. First, the water was flowing through larger volume. See, the sink is providing a huge amount of space to the water, but then when the moment it passes through these holes, it kind of converges. The path available narrows down. That's why this is the example of divergence, but it is negative divergence. And since you can see that the water is curling, you can easily see it. It's visible. The curl of vector functions are normally visible, especially when we see whirlpools in water or tornadoes in air. So this also shows us that even the vector function is curling as well. So the curl here is again non-zero. We can find examples where we have both divergence and curl of the vector function happening. Or sometimes it's only the divergence and sometimes it's only the curl, or sometimes we find both. Usually what happens when the water is flowing horizontally, just following a normal horizontal flow, in that case it has zero curl because it is not rotating. It's kind of a laminar flow. It's just flowing in plain manner. You can see in this case the water is flowing normally. It's in just an ordinary manner. It's simply a horizontal flow of water. And do you see any rotation, any curl of water? No. You can in fact see the plain layers of water which are flowing. There is no rotation. So in case of simple horizontal flow of water, the velocity of water flowing downwards, it's just showing in normal flow. There is no rotation or curl. But if you see the case of this water flowing down through the sink, then you can see that the velocity of water flowing downward, it is showing some circulation. And the moment it shows some circulation, that means there is curl. So that circulation or rotational component which is associated with it, it comes out in the form of whirls. The whirlpools that we call it, the whirls means the rotation, the curls that we see. That is only seen when that rotational component is associated with the flow of water. Here we would say in case of water flowing down through the sink, that curl is non-zero, but here the water which is flowing through the pipe horizontally and it is not showing any rotation or whirls at all, then here we say that the curl is zero. And the curls are actually visible. In case of water, we can see whether the whirls are forming or not. If they are not forming, curl is zero. If they are forming, curl is non-zero. So curl is simply associated with rotation of the vector or circulation in the vector field. Also, if the curl of some vector function is zero, that also implies that that particular vector function is irrotational. And where the curl is non-zero, in that case we say that the vector field is rotational. But here, if the curl come out to be zero, then the vector field is said to be irrotational. Now to understand the curl of a vector function, we just consider a small plane area. For example, say a rectangle. So here ABCD is a rectangle which we have considered in the region of non-laminar vector field. Now what is non-laminar vector field? Laminar means planar, where you can see homogeneous layers. Laminar vector field is that field in which you see homogeneous layers. The partition between all the layers, suppose it's water or any liquid which is flowing, so all the layers of liquid, they are equispaced. There is equal distance or gap between all the layers and they are just homogeneous and uniformly moving. But in case of non-laminar vector field, this is not the case. Here you can see this blue arrows, they actually represent non-laminar vector field, and you can see that the distance between all the layers, these arrows are actually representing layers of the liquid. So the gap is not same. The gap is increasing. Somewhere they are quite close to each other and somewhere they are quite distant, the layers. are quite distant from one another. And at some portion, like here at the top, you can see that the layers are quite congested, quite closely packed. But at some portion down the bottom, you can see there is wide gap between the layers. So the layers are not plainly moving. You can see that the liquid somewhere the layers are quite close together, somewhere there is wide gap, so it is not a laminar flow. In case of laminar flow, all the layers they are equispaced. Like here, these green arrows, they show laminar vector fields. Now you can see how homogeneously all the layers are aligned. There is almost equal gap between all the layers, and all the layer of liquid, they would be flowing smoothly. So that would be a smooth flow. But in case of non-laminar, we just can't expect and estimate what kind of flow would it be. It can get turbulent sometimes when the vector field lines are quite close together, and obviously the magnitude will also be different. In case of laminar vector field, all the vector fields, they are equal in magnitude and they have a particular direction. But in case of non-laminar, in fact the direction also changes sometimes and the magnitude is also different. At some portion, the vector field lines are quite close together. At some place, they are quite distant from each other. So that would definitely affect the magnitude as well. Thus, you can see that in case of laminar vector field, the chances of curl or rotation are negligibly less. These green arrows, they are so perfectly aligned that they won't curl soon. But in case of non-laminar, you cannot say this with certainty. You can't be sure that whether they would curl or not. So there is high possibility for non-laminar vector fields to curl, because since they are showing different behavior, different layers, they are arranged differently, so they might curl at some place, they might not. So that's the reason that whenever we try to understand curl of a vector function, we take non-laminar vector field. We consider a non-laminar vector field and then we say that the curl might happen or it might not happen. Now here in case of non-laminar vector field, the rectangle that we have considered ABCD, when it rotates, then it becomes like the other one. So suppose it rotates, so on rotating, this position is maintained. ABCD, this one, okay? So this is the case. Now, when the vector field is normal to each side of the rectangle, so in this shaded, suppose we say that this rectangle is moving, curl is there. In case of this original ABCD, this rectangle was in the direction of vector field. It was making 0-degree angle with the vector field. But in case of this rotated one that I have highlighted, this is perpendicular to the vector field lines. So basically we have shown this form of rectangle to be 90-degree, to be at the angle of 90-degree to the vector field. So if that's the case, then the line integral round the path ABCD would be what? What would it be if we try to find line integral? How do we find line integral? Line integral means single dimension. And of course, we would find it of some vector, which is our vector field A. This is the vector field A that we have shown. And then line integral would be with respect to the position vector dr and then this thing. We know this, how to find line integral, A dot dr. And what is this A dot dr? This is dot product. So basically this would be A dr cos theta. So when your theta is 90-degree, the line integral would be 0, because cos 90-degree is 0. Thus we know that when this ABCD rectangle, it rotates, and when it reaches the position when it is perpendicular to the vector field lines, or when we say that the vector field lines, they are normal to each side of the rectangle, in that case the line integral would be 0. What about this position? The one I'm highlighting in pink. In this case, the rectangle is aligned in the direction of vector field. But still you can see that the sides BC and AD, they are perpendicular to the vector field. We are concerned with line integral. So we have to see which side is in the direction of vector field and which side is perpendicular to the direction of vector field. Now you can see both BC and AB, they are perpendicular. So now I have highlighted these two sides with red color, and these both are perpendicular to the vector field A. Once again they are perpendicular, and once again if we find the line integral, because theta is 90 degree for these two sides, the line integral for these two would be 0. So this is what I mean by this, that A dot dr for side AD and A dot dr for side BC would be 0, even in this condition, when rectangle is aligned in the direction of vector field A, because AD and BC sides are perpendicular to the vector field. They are still perpendicular to vector field, and perpendicular means theta is 90 degree, and we are taking dot product. So the expression for dot product is ADR cos theta, and when theta is 90, that means cos is 90 degree, and cos 90 is 0, so our line integral would come out to be 0. But what about AB and CD sides? Well, they are totally aligned in the direction of vector field. That means here the theta is 0 degree. So let me mention here theta 0, and here also this theta is 0 degree. In that case, what would be the line integral? Well, it would be something. So if I mention this A dot dr for side AB and for side CD, then we would get some finite value. The value could be ADR. We can say that the value would be this ADR, and then definitely we would integrate it over the limits, and here A and dr, they both are magnitudes, right? Because theta is 0 degree for these two sides and cos 0 degree is 1. So here we would get some finite value. That means the line integral for two sides A, B and CD of the rectangle would give us some finite value, and the line integral for the two sides A, D and BC, which are perpendicular to the vector field, that would give us 0. Thus we say that we would get some finite value of line integral, because AB and CD, they are at different positions. You can see different height. So definitely the components along AB would be different than the components along CD. So there would be some difference in values, and we would get some finite value for these two sides. Thus here what we did was we took vector field and we considered some area, and that area was rectangle. We considered a two-dimensional figure here. And now this statement is very important, which state that we find that the value of line integral round the boundary of the area. Yes, what we did was we found the line integral round the boundary of the area, and area was rectangle. So it depends upon the orientation of the area. Orientation of the area with respect to the field. That in what direction the area is aligned with respect to the field, and then it has maximum value for a particular orientation, like we did here, and we got to know that when that area was aligned in perpendicular direction, the value of line integral was coming out to be 0, and when that area was aligned in the same direction as that of the field, then the value came out to be 1. So that was the maximum value. So that means when we have area and we are finding line integral around the boundary of that area, the value of the line integral actually depends on the orientation. Nothing else matters. Not even how much area is there. That would definitely give you some finite value, but the main thing that matters here is the orientation of the area. And what is orientation? Orientation means in what direction the area is aligned with respect to the field. Like here, you can see that if it is oriented in the same direction, that means our angle is 0 degree. In that case, cos 0 degree will give us 1. If it is aligned in perpendicular direction, then a cos 90 degree would be 0. If it is aligned in the opposite direction, that is when our angle is 180 degree, in that case cos 180 degree gives us -1. In case of 270 degrees, again the value is 0. And when we have cos 360 degree, or we say when the area has actually made one complete rotation, so it has come back to the original state. So whether you call it angle 0 degree again, or you call it angle 360 degree, the value is still 1. Cos 0 degree and cos 360 degree both are 1. So this is the meaning that the orientation really matters. The direction in which the area is held with respect to the vector field. And how do we guess that what is the orientation? In what direction the area is held? That totally depends on the rotation of that area. That in one part, is there any rotation in the area? Because if that particular area is rotating, only then we can have different cases. The cases when it would be aligning in the direction of the field, sometime it would be at some angle with respect to the field, in some case it would be normal to the field. So that only depends, and we can find this particular thing only and only if that particular area is rotating. That means if curl is involved. And that's the reason why we considered an area to understand curl of a vector function. And again now, this example that we took, the consideration that we made is really important to understand curl better. The way we know that whenever we talk of divergence, the two integrals which are of use are surface integral and volume integral. Both have the relation whenever we talk of divergence. Similarly here, now we know that whenever we talk of curl, the two integrals that would be involved will be area, that means surface integral, and the line integral, because it all depends on the area, the way area is aligned with respect to the field, and also the line integral, that what is the shape of the area. Like we would get different result for square, we would get different result for a circle or for rectangle, and so on. So the shape of the area also matters, and the shape is defined by the boundary of the area. Whatever is the boundary of the surface that we have considered, that would give us some answer. And boundary is related to line integral, you know that. So, and area, if we are concerned with the area also, because how much portion of the field is covered by that area, then for that we need to find surface integral. So now remember that whenever we talk of curl of a vector function, two integrals that would be of use will be surface integral and line integral. Let's write down the exact definition of curl of vector field now. It states that the curl of a vector field at any point is defined as a vector quantity, because we know curl of a vector field gives us a vector quantity again. So definitely it's a vector quantity whose magnitude is equal to maximum value of its closed path line integral. Closed path line integral. See, in case of rectangle, we try to find the line integral of all the sides. So the line integral of all the sides combined would give us closed path line integral. If we want to find the line integral along the all sides of the rectangle, when we say that line integral along the closed boundary ABCD, then we would say then that is equal to line integral along AB plus line integral along BC plus line integral along CD plus line integral along DA, out of which the line integral along BC and DA is 0. So we would be left with only the line integral along AB and CD. So thus the curl is a vector quantity whose magnitude, because of course if it's a vector quantity, so both magnitude and direction would be of importance. So magnitude is equal to maximum value of its closed path line integral per unit area, because the area really matters. Whether your area is or that of a rectangle or a square or a triangle or any irregular polygon it is. So that really matters. So per unit area, we have to mention. The way we used to say that in case of divergence, it's the surface enclosed, or we call it the surface integral of a vector field per unit volume. In that case, we used to say per unit volume, and here we are saying the line integral of that vector field per unit area along the boundary of an infinitesimal plane area around that point. Whenever we consider very small elements and whose direction is perpendicular to the plane of test area when it is in a position of giving maximum circulation. When we find maximum circulation, that means when the angle is maximum between the area and the vector field. In that case, that particular direction which is perpendicular to that situation would be the direction of curl of the vector function. So if we have to write it down mathematically, then that means first we are saying closed path line integral. So line integral would definitely be of the vector function A. So this is the way we write it down. And then it is saying closed path line integral. So this single integral is the representation of line integral, but we are saying closed path line integral. So that means we have to put circle over here. And then it is saying maximum value of its closed path line integral. So here I'm going to write down the maximum value. We have to pick the maximum value along the boundary of an infinitesimal plane area around that point and whose direction is perpendicular to the plane of test area. And we know that if we have an area, then the direction perpendicular to that area is what? It is n cap. We know the unit vector is always defined perpendicular to the surface that we are considering. And then perpendicular to the plane of test area when it is in a position of giving maximum circulation. So this delta S is important because we have to consider for that particular area, and then we have to put this limit delta S tending to 0, the way we put the limit delta V tending to 0 in case of divergence. Why? Because here we have said that we are considering infinitesimal plane area. So that area that we have considered is very small. So the delta S, that means whatever is the area enclosed, captured, that is very small. So delta S tends to 0. This is the mathematical definition of curl of a vector function, and n cap is again the unit vector along the normal to the plane of test area. We also call curl sometimes circulation. We also call it rotation or simply rot. The name circulation comes from circulation of a liquid. We usually say water is circulating, and that is when it is having some rotational motion. So that's the reason that whenever something rotates, usually the path followed is a circular path or almost circular path. That's the reason we have picked these words, just to give an idea. Circulation, rotation, rot, they are the words that we use for representing curl, and sometimes we use this in other cases as well, but mainly just to give an idea that something is rotating, something is moving, and that happens in case of non-laminar fields, because we know in case of laminar they are just moving smoothly one over the other. The layers are just flowing in a plain manner and they won't rotate. But where we see the whirlpools, that means rotation is occurring, and definitely there would be some non-zero curl of the vector function involved. So this was all about the physical significance of curl of a vector function, And now the way we understood divergence in terms of Cartesian coordinates, similarly, we are going to understand curl of a vector in terms of Cartesian coordinates in our next video. That's all for today. Thank you.